let's move on now to some power statistics. Statistical power usually refers to the probability that a test correctly rejects the null hypothesis when the null hypothesis is false, okay? So it's related to sample size. The bigger the sample, the more likely you are to correctly reject the null when the null is false. But it's also connected to other parameters, and you need to consider this when you're designing a randomized control trial, because you can tune a lot of these parameters. So power in this case is going to be 1 minus the probability of type 2 error. If you remember from stats class, type 1 error, okay, is the one that is associated to the p-value, okay? So it's the probability of rejecting the null hypothesis when the null is true, okay? And that is basically alpha. Type 2 error, on the other hand, is the probability of rejecting the null hypothesis when the null is false. So this would be like a false negative, and the first one would be a false positive. Okay. So again, you have type 1 error, type 2 errors. Let's look at this. Again, type 1 error, if you think about this, is the probability that this sample and this sample comes from the same sort of distribution, right? Given that they're so far apart, okay? Because they're so far apart, that means that most likely they come from different distributions, okay? So that's why the p-value here is 0.02, okay? And that would be a type 1 error in this case, because even though the p-value is low and you would reject the null is true. They both come from the same distribution. By the way, these are great illustrations by Alison Horst, which is the art testing resident from our studio. You should check her out, which is pretty cool. Type 2 errors, on the other hand, is basically the contrary. These two samples come from different populations, population 1, population 2, but they're kind of like meshed together, okay? So you can't distinguish them, okay? So in this case, you would not reject the null, even though the null is false, okay? This is the typical picture that we see for statistical power, okay? So again, assume that this is the null. Usually the null is centered in 0, so basically the null is that there's no effect. And then you have an alternative hypothesis, okay? That will be H sub A, okay? Alpha, which is usually the p-value, is this tail right here. Sorry, alpha, which is the significance level that we usually want, which is usually 5%, right? 0.05. Is the tail right here. I mean, half of this is the tail. Remember that this is symmetrical. The power in this case is beta, which in this case would be the orange region, and 1 minus, beta would be the type 2 error, right? And the power here would be 1 minus beta, okay? And beta is the, again, type 2 error, okay? 1 minus beta is the power. Usually we fix the power to be like 80 or 90% in that sense. Again, but the idea is that we don't want either to make type 2 errors or type 1 errors, okay? And this will depend a lot on different parameters that we have. So one of those parameters that is most important is how big of a sample do I need, okay? So let's assume that we have a training program that causes the income to rise by $40, okay? So again, we have different people here that were assigned to treatment and control group. You have their income before, their income after, and you can see the difference. You can estimate the effect. And basically you can see that people that were assigned to the training program actually increased their income by $40. Great. What happens if for the same experiment, I only enroll 10 participants? If there's no difference, and this is my null in that case, basically I cannot distinguish whether this is an effect, like a real effect or not, right? My p-value in this case is 0.8. This happens because my null hypothesis is super wide because I have very few participants. Okay, so I have a lot of sampling variation. This is basically simulating a world when there's no treatment effect, and I just randomly take out 10 people where there's no effect and just plot the difference between the treatment and the control group. Again, assuming that there's no effect. And as you can see, I cannot detect the effect. What happens now if my sample size increases to 200? As you can see, my null actually reduces a lot, becomes way more, way less spread out. And now my value of 40 is much more extreme. So basically I can reject the null in this case with a p-value of less than 1%, while in a world with 10 participants, I could not. So again, the sample size of your study matters, but a lot of other things matter as well. Okay, so it depends on the power that you want to have. It depends also on the expected size of the effect that you want to identify. All of those things. Okay, so the best thing here is to use a statistical power calculator to make sure you can potentially detect an effect. And in that sense, you can move a lot of different things. You can move your sample size, you can move how many people you assign to treatment or to control. All of those parameters will affect your power calculations, okay? Basically, what the statistical power calculator does is assume that you have large enough sample sizes and relies on probability theory, which is not important here in this case. Just know that you can use sort of these tools to do so, okay? Another way that you can do it is also use simulations. So basically what we did here before, this was running simulations. So I'm assuming, again, that I'm on a world where there's no treatment assignment, there's no effect. So with the data that I have, I basically just randomize the treatment with random allocations. And I compare it to the actual effect that I observed in my data. This also brings us to a quick note on randomization inference, which is also important. So as I mentioned, previous power calculations work well on large samples or large enough samples, okay? But on smaller samples, usually we can't rely on the central limit theorem. So a lot of these formulas and probability theory sort of falls apart. And I also think that randomization inference is a good way to think about how the whole process of randomization works, even if you don't necessarily use this for power purposes. So randomization inference, what it is basically is it estimates what are the chances of something happening given all possible randomization scenarios. So in the case of the simulations, I'm not randomizing every randomization scenario because there's a lot, but with simulations you can sort of get close enough to, or a large enough number that sort of approximates what the p-value would look like, okay? But in this case, what we want to do is actually we will estimate all randomization scenarios. So let's talk about this canonical example, which is the lady tasting tea. So there's a lady in England who basically says that she can always know whether tea or milk were poured first in a cup. Okay, so you decide to test whether she's telling the truth or not. And for that, you run an experiment. So imagine you have 6 cups of tea. And on the first 3, you put milk first. And on the last 3, you put tea first. And then you give those to this very knowledgeable lady and ask her to identify which are the milk cups and which are the tea cups. So as you can see, this is only one of the random allocations that I could have used. There are actually 19 other combinations. So with 6 cups and 2 assignments, there's actually 20 combinations, which is n chooses k. So in this case, 6 chooses 2. So as you can see, we have 3 with milk first, 3 with tea first, but I could have gone milk, tea, milk, tea, milk, tea, or milk, milk, tea, tea, milk, 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 tea. You get the gist. There's a lot of different combinations, so this is just one of them. So the idea here is that I have this treatment allocation that I chose, but all of these other ones are equally as likely, right? So I have 3 milk, 3 teas. I could have 1 milk, 1 tea, 1 milk, 1 milk, 1 tea, 1 tea, etc. And you have actually 20 different scenarios that you can do with this. We're just testing one of them. So the idea here is that if the woman is telling the truth, then she needs to pick out the 3 cups of tea with milk first, right? So you're asking her to, out of the 6 cups that you gave her, please pick out 3 that have milk. And she actually does it, okay? So what are the chances that she just guessed? So this is basically where the randomization inference comes in. How likely or unlikely is that she actually did not know? So basically we're under the null assumption that she doesn't know. There's no effect. What are the chances that she just guessed it? That she just guessed this allocation? So if she's just guessing, then she's equally likely to choose any of the 20 possibilities, right? Because there's 20 different ways I could have randomly allocated the treatment. So under the null hypothesis, and again, the null hypothesis is she does not know what has milk and what has tea first. The probability of her of choosing k correct ones out of n cups, okay, so basically having k successes, is 1 over the total number of permutations, which in this case again is 20, times n chooses k times n chooses n minus k, which basically means it's 1 over 20 in this case, times choosing k correct ones and failing in n minus k ones. Okay? So in this case, the probability of choosing all of them correctly is just 1, right? Basically, there's only one way that she could choose all of them correctly. There's no other, there's basically no other combination that can give you 3 correct ones. So that's 1 over 20. The probability of getting 2 correct, however, is 9 over 20 because she could have chosen 3 and just by chance, there's 3 different ways that she could have chosen 2 correctly. The same thing with 1 correct. And the probability of getting actually none of them correct is also 1 over 20. Okay, so we get a p-value of 0.05. So if we're thinking that we're rejecting everything under, 10%, then basically it would be very rare in this case with 6 cups that she would have just randomly chosen the correct ones if she did not know which the correct ones were. Okay, so that's the idea of randomized inference. How likely or unlikely is this to just happen by chance if the null is right, meaning if she does not know what she's talking about? Is a 5% chance. That's very low, okay? So we are assuming that because this is very low, then she is actually telling the truth, okay? And she knows how to distinguish tea first versus milk first. So we're going towards the, so we're rejecting the null and going towards the alternative hypothesis. That is that she does know what's happening. Great. Good. Now let's move on to limitations and potential problems in randomized controlled trials. Let's talk first about generalizability of the randomized controlled trials. This is something that Angus Deaton talked about in the video that you had to watch. And it's basically this idea of external validity versus internal validity. External validity means basically relates to the extent to which results can be generalized to other contexts or populations, giving your field experiment results. And internal validity is the extent to which the observed results actually represent the truth in the population that we're studying, okay? So this doesn't necessarily mean that we want to generalize, but for the population that we're studying, meaning like the sample at hand that we have, what is the extent that the observed results actually represent the truth, meaning are unbiased and consistent. So let's define this a little bit more simple. So first, what we do in a randomized experiment is that we have a population and we define eligible units, right? So for instance, if you're doing a randomized control trial just in the US, your eligible units will be just people that are in the United States. If you're doing it just in a city, or if you're doing it just for females, or if you're doing it just for like children, things like that, that would be your eligible units, right? And this is basically the population that you want to generalize your results towards, most likely. And this basically relates to external validity, when you go from your eligible units to your evaluation sample. The problem here is that if this, for instance, your evaluation sample is just a random sample of your population, then this is great because you will have external validity, most likely. You will be representing, but you will be basically selecting as just a mini version of the population that you want to make inference for. The main problem is that a lot of the time in field experiments, we use what is called a convenience sample. So basically, either people that you think are easier to recruit for an experiment, or even people that actually consent to an experiment, which also was part of the JIT that we were talking about, the last JIT that we had, about that Netflix study. People had to consent to be on the study, and those people might be different to the people that you want to generalize for, okay? So if your evaluation sample actually doesn't resemble your population, then you basically lose this external validity, which doesn't necessarily affect your internal validity or your the estimate that the effect that you're measuring, but you need to know to what population that effect refers to. So in this case, internal validity is given by randomization. So you're randomizing some people into treatment, some people into control, and again, those two groups are comparable. So if everything is done well, then you have an internally valid study. What you might not have is an externally valid study if this population does not resemble this one. And that is some of the main problems with external and internal validity. And this is something that Angus Deaton was talking about with respect to how can you take results from a certain population in a certain country and actually extrapolate it to another population. Long story short, you usually can't, okay? There's certain adjustments that you can make, and we're gonna talk about it next week. We can do some sort of reweighting and things like that. But it is way easier a lot of the times to actually fix this by design than fix this by post adjustments. So one important thing that you would need to consider if you are actually designing a field experiment is one, try to clearly define which is the population that you want to estimate an effect for. Two, do your best to recruit widely, okay? So again, even stratify and try to recruit from each of these different groups, generate wide incentives so people are not so focused for the ones that actually consent to the study. And again, cast a wide net in that sense. Don't try to rely always on that convenience sample, or like even worse, like your friends or people that you know, or things like that. Try to go beyond that. That helps a lot to for generalizability. Okay. Great. Other common problems are non-compliance and attrition. Okay, attrition basically means that units fall out of your sample. So basically, you randomize them into treatment and control group, and for instance, then you go and try to measure something in the control group, and you can't find them. Okay, they just disappeared. If you're running a survey, they wouldn't answer the phone. They wouldn't come back for a follow-up interview or things like that. Or even like if you're using administrative data, for some reason they're not there anymore. Okay, you can't follow them. So those are some examples of attrition. And basically, one of the problems of attrition, if attrition is correlated in some sense to other covariates, then this could bias your results, because basically you would have a self-selected outcome now, because you can't observe the outcome for everyone. You will just observe it for the sample that did not attrit. Okay. What you can do in this case, again, is try to give incentives for people to come back. You don't really care if some people fall out, as long as there's not systematic sort of fallout of your sample. So if the treatment and the control group kind of like you lose 5 or 10% of your sample in both sides, you can assume that they're missing at random. And if they're missing at random, then you again lose sample size, lose power, but you're not getting bias, okay, which is the important part. The problem again, if for instance your control group attributes more than your treatment group, then that would generate bias. Again, what you need to do if the control group doesn't have enough incentives to come back for a follow-up or a survey, or for some reason you're scared that they will fall out of your sample for some reason, is again generate the incentives or try harder to reach that group than the treatment group. Okay. But again, you should always check the balance of missing values or non-response between your treatment and control group in the outcome after randomization. Non-compliance, on the other hand, basically refers to the fact that units that were assigned to one group end up in another. So example for this is, for instance, sometimes you have school lotteries and you offer a slot in a school to a kid, and that would be that they're offered the treatment, they were assigned to the treatment, but they end up, for instance, not taking it. Okay, so they were assigned to treatment, but they did not actually comply with the treatment. They ended up in the control group, even though they were assigned to treatment. And the other way around would be a kid that was not initially offered a slot in a school, and for some reason someone knew someone and they ended up at that school anyway. That kid was assigned to control, but for other reasons outside the randomization, they ended up in the treatment group. So all of that, the non-compliance doesn't necessarily, again, affect our internal validity. So this is the same thing as we saw in the get out the vote example, where people were assigned to treatment and they were assigned to be contacted, but they were actually not able to contact them. That would be an example of non-compliance. Okay, so it doesn't again affect the internal validity if we use the variable that was randomly assigned as the main sort of regressor. So in that case would be treatment assignment and not necessarily treatment take-up. If you take treatment take-up and there's no compliance, then you will have biased results. If you take treatment assignment and you regress that, then you will not get an average treatment effect, but you would get an intention to treat, and that would be unbiased. Okay, and a lot of the times intention to treat is actually what you want. As we mentioned before, a lot of the times you can't actually force people to take treatment. You can only offer it. Okay, so a lot of the times what you actually want is what's the effect of me offering the treatment, because I cannot force people to actually take it. So that's something also that it's good to know. So again, keep in mind in attrition and non-compliance, when this is a problem, how you can solve it, all those things are important. So this is just to reiterate, if attrition is actually correlated with the treatment, then we're in trouble, okay? Because basically, then the treatment, the outcome would be correlated with the reason they are treated, and the reason they are treated might be correlated with the treatment assignment as well, okay? So the ignorability assumption can break. Non-compliance is a problem for identifying the average treatment effect. So treatment assignment is random, but not necessarily the take. Other problems that are important to look out for are Hawthorne effects, for instance. This is not quite relevant. This is not quite relevant. This is doesn't come up that often, but is also, depending on the experiment that you're running, something to look out for. Hawthorne effects is effects that occur when people behave differently because they're being watched. So, for instance, just because you are conducting an experiment, people kind of change their behavior. So this would have a problem with generalizability of your results, right? And the Young-Henry effects also are effects that occur when control group works harder because they were not assigned to treatment. So basically they're trying to prove something, and that might actually bias your treatment effects downwards, right? You might not find actually a correct treatment effect because just your control group is kind of stepping it up because they were kind of denied a treatment. So there are ways to sort of try to help this by design. So try to not be very salient in the watching stage of an experiment. Okay, try to be very kind of hands off, to not generate a Hawthorne effect problem. With Young-Henry effect, a lot of the times, depending on the scenario, what you can do is think about offering the treatment afterwards. Okay, so telling people like, you're not getting it right now, but like in a next wave you will get it. So then people won't feel like left out in that sense. Another important issue a lot of the times with randomized controlled trials is the feasibility. Randomized controlled trials can be expensive and also can be slow. A lot of the times, if you're conducting experiments that are kind of like take into account like longer run outcomes, they can take a long time actually to see some results. So that's why they're not always the best thing to do, especially if you need to take action quickly. And sometimes just organizations might not be willing to randomize. A lot of the times they're set on their ways in terms of like, I want to select people based on a certain score or certain things like that, and I don't want to randomize. Okay, so what can you do about that? Getting around some of these issues, especially the unwillingness to randomize a lot of the times. The first one is taking up a staggered adoption. So it's similar to the example that I gave for the Young-Henry effects. So eventually you propose to treat everyone, but at different times. So basically you can think about this when you have panel data. So you have units that you observe at different points in time. And at first you treat some units, and then you treat other units, and then you end up, for instance, treating everyone. But for certain time periods, you can actually have small sort of randomized trials for those units. This doesn't work if you need to follow up like in long term, basically because in the long term everyone's gonna be treated. But if you're just looking at shorter term outcomes, this is a good solution. The other solution also is randomizing the bubble. So basically the example I was giving, that people have a score and they don't want to like budge in that. So for instance, if you're thinking like a university that has an SAT cutoff, right, of, I don't know, 750. They might really not want someone that's like at 250, and they might not really want to lose someone or not give admission to someone that has, I don't know, 1400, right? So in that sense, you can you can offer to randomize someone that it's on the margin of actually receiving the treatment. So if their cutoff is 750, why don't we randomize people that are like above 600, below, I don't know, 950, right? So in that sort of bubble, people kind of look the same or not look that different. You're definitely not offering admission to someone that is very low down the distribution, and you're not taking away admission for someone that is very high up in the distribution. But those people that are kind of in the margin of being admitted or not, you can randomize those. So that is also an option. In terms of staggered adoption, this is usually what it looks like, okay? So for instance, here we have 3 time periods, okay? So in the first time period, we can treat group 1 and not treat, we can treat group 4 and not treat group 1 to 3. On period 2, we can treat group 3 and 4 and not treat group 1 and 2. And finally, in the third period, you can not treat group 1 and treat 2, 3, and 4. So if you look at this, basically what this means is that, for instance, if you take period 1 and 2 and group 1, 2, 3, what you have here is a mini randomized control trial, right? You have this control group, which is group 1 and 2, and then you have group 3, which will be a treatment group in period 2. So you have pre-treatment covariates here, right? And then you have post-treatment covariates or outcomes here, and you have one treatment group, okay? So this is important because you have a variation between not being treated and then being treated, and then you have a pure control group that you can use in this case, okay? So in this case, again, your outcome variable would be some outcome on period 2, and your covariates could be certain covariates that you think are important that are measured on period 1. Remember that your covariates need always to be before the treatment was assigned, because they cannot be affected by treatment. If not, they could be a collider. Okay, and the same thing if you look right here, right? It's the same. It's the same idea. You have group 1 that was never treated, and you have group 2 that was not treated on period 2 but was treated on period 3. So again, in this case, you have your treatment group, which would in period 3, that would be group 2, a control group, and you can measure covariates on time period 2.